In this video, we will be discussing tectonics and earthquakes. Earth is about 4.6 billion years old. The geologic timescale is a summary timeline of all Earth history. It names the time intervals for each segment of Earth's history from vast eons through shorter eras, periods, and epochs. Breaks between some of the major time intervals also mark the 5 major mass extinctions. A guiding principle of earth science is uniformitarianism. This basically tells us that the present is the key to the past, which assumes that the same physical processes active in the environment today have been operating throughout geologic time. For example, if streams carve valleys now, like we see in this slide, they must have done the same thing 500 million years ago. Evidence from the landscape record of volcanic eruptions, earthquakes, and processes that shape Earth's surface support uniformitarianism. Although the ages and types of rock differ from place to place, the processes that form, erode, and deposit these rocks and sediment are uniformly similar. Along with the other planets in the Sun, Earth is thought to have condensed from a nebula of dust, gas, and icy comets about 4.6 billion years ago. As Earth solidified, gravity sorted materials by density. Denser substances such as iron gravitated slowly to its center, and less dense elements such as oxygen, silicon, and aluminum slowly welled up toward the surface and concentrated in the crust. Consequently, Earth's interior is sorted into roughly concentric layers, each one distinct in either chemical composition or temperature. Earth's core is nearly twice as dense as the mantle because it is composed of denser metallic iron-nickel alloy. At Earth's center lies a dense metallic core, divided into an inner core and an outer core. The core makes up 1/3 of Earth's entire mass, but only 1/6 of its volume. The inner core of solid impure iron is well above the melting temperature of iron at surface conditions, but it remains solid because of the tremendous pressure caused by the weight of the overlying materials. The outer core is molten iron and has a lower density than the inner core. The rotation of the Earth affects the fluid outer core, and this is what generates the Earth's magnetic field. Recall from earlier videos that the magnetosphere surrounds and protects Earth from solar wind and cosmic radiation. A compass needle points to magnetic north because of Earth's magnetic field. Above the core lies the mantle, a layer of hot but mostly solid material that represents 80% of the Earth's total volume. The mantle is rich in oxides of iron and magnesium and in silicates. The extremely high temperature and pressure in the lower mantle softens and deforms solid rock material over millions of years. Rocks in the warmer lower mantle rise upward where they slowly cool as their heat is transferred to the upper mantle. As the rock material cools, its density increases, and the rocks begin to sink and move downward, also aided by gravity. The up and down movement of rock material in Earth's interior is the result of these convection currents, which power the process of plate tectonics. In the upper mantle, closer to Earth's crust, the temperature and pressure decline, so the rocks are more rigid. The asthenosphere lies just below the lithosphere and extends from about 70 kilometers beneath Earth's surface to a depth of 250 kilometers, or about 43 miles to 155 miles. The asthenosphere is the least rigid part of the mantle, and geologists describe the rock of the asthenosphere as being plastic. This means that it is weak material that can bend or flow slowly over long periods of time. The asthenosphere contains pockets of increased heat from radioactive decay. This partly explains why about 10% of this layer is molten in uneven patterns in hot spots, and why slow convective currents occur. The resulting slow movement in the asthenosphere disturbs the overlying crust and creates tectonic folding, faulting, and deformation of surface rocks. The Earth's surface is constantly building up and breaking down. while the internal forces such as plate motions and volcanism build landforms. Surface processes such as weathering and erosion work to reshape them. Although the processes occur slowly over geologic time, the result is a restless planet where these two opposing forces interact in a process called the geologic cycle. Earth's internal heat and external solar energy fuel the geologic cycle, which is also influenced by the force of gravity. Three subcycles compose the geologic cycle. The rock cycle, explained in the next section, produces the igneous, metamorphic, and sedimentary rocks found in the crust. The tectonic cycle brings heat energy and new material to the surface and recycles material, creating movement and deformation of the crust, as we can see in this slide. The hydrologic cycle processes earth materials with the chemical and physical action of water, ice, and wind. The rock cycle is a natural recycling process by which rocks form and then over time change and reform into another type of rock. To understand the rock cycle, you need to become familiar with basic earth materials, elements, minerals, and rocks. 8 natural elements: oxygen, silicon, aluminum, iron, calcium, sodium, potassium, and magnesium, compose 98.5% of the Earth's crust by weight. These elements combine to form many minerals. A mineral is an inorganic or non-living natural substance with a specific chemical formula and usually a crystalline structure. A rock is an assemblage of minerals, including mineral and organic matter bound together as part of the lithosphere. A series of processes called the rock cycle form 3 groups of rocks. These are igneous rocks, sedimentary rocks, and metamorphic rocks. Igneous rocks form from material that melts under the high temperature and pressure found inside the mantle and crust. Igneous rocks are further subdivided into 2 types: intrusive and extrusive. Intrusive igneous rocks form from mantle material injected into the crust, where it cools and hardens beneath the surface. Extrusive igneous rocks form through volcanic activity when molten material from the mantle melts through the crust and onto Earth's surface, where the molten material then hardens into solid rock. Sedimentary rocks often form from fragments of eroded rocks or sediments that are deposited in low depressions like valleys or lakes and oceans, and then they are compacted to form new rocks. Metamorphic rocks are any rocks that chemically reform under tremendous pressure and heat, and this occurs as a result of being deeply buried inside the crust. The igneous process. Lava is magma that reaches the surface. Either magma intrudes into crustal rocks, cooling and hardening below the surface to form intrusive igneous rocks such as granite, or it extrudes onto the surface as lava and cools to form extrusive igneous rocks such as basalt. The texture of igneous rocks is based on the size of their crystals, which is directly related to how the rocks formed. Slow cooling, intrusive igneous rocks such as granite have larger, coarse-grained crystals. Faster cooling rocks result in smaller, fine-grained crystals, as in extrusive igneous rocks such as basalt and rhyolite. Igneous rocks make up 90% of the Earth's crust, although sedimentary rocks, soil, or oceans frequently cover them. Sedimentary process. Most sedimentary rocks form when eroding fragments of existing rock or organic materials are transported downslope by water, ice, wind, and gravity. Metamorphic processes. Metamorphic rocks have undergone intense heat and pressure that alter their physical and chemical properties. This process typically makes rocks harder and more resistant to weathering and erosion. Regional metamorphism occurs when rocks buried inside the crust are subjected to high temperatures and pressures over millions of years. This can take place when rocks compress during tectonic collisions between slabs of Earth's lithosphere. The shearing and stressing along earthquake fault zones is another cause of metamorphism. Okay, I'm going to stop there. Thank you, and I will see you in the next video.